Welcome to the course of Statistics for Data Science and Business Analysis. Part 2 discuss about the normal distribution, central limit theorem, estimators, and estimates, standard error, margin of error, t-distribution and calculating confidence intervals. Part 2 discuss about the lectures such as, Lecture 14, Introduction to Inferential Statistics, Lecture 15, Distribution, Lecture 16, Normal Distribution, Lecture 17, the Standard Normal Distribution, Lecture 18, Understanding the Central Limit Theorem, Lecture 19, Standard Error, Lecture 20, Working with Estimators and Estimates, Lecture 21, Confidence Intervals, an invaluable tool for decision-making, Lecture 22, Calculating confidence intervals within a population with a known variance, Lecture 23, Students' t-distribution, Lecture 24, Calculating confidence intervals within a population with an unknown variance, Lecture 25, What is a margin of error and why is it important in statistics? Lecture 26, Calculating confidence intervals for two means with dependent samples. Lecture 27, Calculating confidence intervals for two means with independent samples Part 1. Lecture 28, Calculating confidence intervals for two means with independent samples Part 2. Lecture 29, Calculating confidence intervals for two means with independent samples Part 3. Lecture 30, Practical example _ inferential statistics. Lecture 14, Introduction to Inferential Statistics.
Now that we have covered the basics of descriptive statistics, it is time to move on to inferential statistics. Inferential statistics refers to methods that rely on probability theory and distributions, in particular, to predict population values based on sample data. While this definition may not be clear just yet, starting from the next lesson, we will define what a distribution is and will go through a couple of distributions you will likely use at work. This will naturally lead us to point estimates, and we will conclude the section with confidence intervals. We will not only present these topics, but will also develop a deep understanding of the statistical processes. This will help you a great deal if you get into data science. I recommend you complete all the exercises provided, as they will reveal additional subjects you will be in charge of researching. These insights will likely be your gateway to the fundamentals of quantitative research and data-driven decision-making. Finally, to get you more hyped about what's to come, Udemy, the world's most popular e-learning website, was making decisions about its strategy based on the methodology that's to follow in this section. Good luck with the lessons, and have fun!
Lecture 15, Distribution.
Before we can talk about testing, we have to learn what a distribution is, and in this lesson, we'll do just that. In statistics, when we use the term distribution, we usually mean a probability distribution. Good examples are the normal distribution, the binomial distribution, and the uniform distribution. Alright, let's start with a definition. A distribution is a function that shows the possible values for a variable and how often they occur. Think about a die. It has 6 sides, numbered from 1 to 6. We roll the die. What is the probability of getting 1? It is 1 out of 6, so 1/6, right? What is the probability of getting 2? Once again, 1/6. The same holds for 3, 4, 5, and 6. Now, what is the probability of getting a 7? It is impossible to get a 7 when rolling a die. Therefore, the probability is 0. The distribution of an event consists not only of the input values that can be observed, but is made up of all the possible values. So, the distribution of the event, rolling a die, will be given by the following table. The probability of getting 1 is 0.17. The probability of getting 2 is 0.17, and so on. You are sure that you have exhausted all possible values when the sum of the probabilities is equal to 100%. For all other values, the probability of occurrence is 0. Each probability distribution is associated with a graph describing the likelihood of occurrence of every event. Here's the graph for our example. This type of distribution is called uniform distribution. It is crucial to understand that the distribution is defined by the underlying probabilities and not the graph. The graph is just a visual representation. Alright, now think about rolling 2 dice. What are the possibilities? 1 and 1, 2 and 1, 1 and 2, and so on. Here's a table with all the possible combinations. We are interested in the sum of 2 dice. So what's the probability of getting a sum of 1? It's 0, as this event is impossible. What's the probability of getting a sum of 2? There is only one combination that would give us the sum of 2, when both dice are equal to 1. So, 1 out of 36 total outcomes, or 0.03. Similarly, the probability of getting a sum of 3 is given by the number of combinations that give a sum of 3 divided by 36. Therefore, 2 divided by 36, or 0.06. We continue this way until we have the full probability distribution. Let's see the graph associated with it. Alright, so looking at it, we understand that when we roll 2 dice, the probability of getting a 7 is the highest. We can also compare different outcomes such as the probability of getting a 10 and the probability of getting a 5. It's evident that it's less likely that we'll get a 10. Great! The examples that we saw here were of discrete variables. Next, we will focus on continuous distributions, as they are more common in inferences. In the next few lessons, we'll examine some of the main types of continuous distributions, starting with the normal distribution.
Lecture 16, Normal Distribution.
Okay, here we go. So far, we learned that the distribution of a dataset shows us the frequency at which possible values occur within an interval. We also said that there are dozens of distributions. Experienced statisticians can immediately distinguish a binomial from a Poisson distribution, as well as a uniform from an exponential distribution in a quick glimpse at a plot. In this course, though, we will rather focus on the normal and students' t-distributions due to the following reasons. They approximate a wide variety of random variables. Distributions of sample mean with large enough sample sizes could be approximated to normal. All computable statistics are elegant. Decisions based on normal distribution insights have a good track record. If it sounds like gibberish now, I promise that things will be much easier once we get started. Here is a visual representation of a normal distribution. You have surely seen a normal distribution before, as it is the most common one. The statistical term for it is Gaussian distribution, but many people call it the bell curve as it is shaped like a bell. It is symmetrical, and its mean, median, and mode are equal. If you remember the lesson about skewness, you would recognize that it has no skew. It is perfectly centered around its mean. Alright, so it is denoted in this way. N stands for normal. The tilde sign denotes it is a distribution, and in brackets we have the mean and the variance of the distribution. On the plane, you can notice that the highest point is located at the mean, because it coincides with the mode. The spread of the graph is determined by the standard deviation. Now, let's try to understand the normal distribution a little bit better. Let's look at this approximately normal distributed histogram. There is a concentration of the observations around the mean, which makes sense as it is equal to the mode. Moreover, it is symmetrical on both sides of the mean. We used 80 observations to create this histogram. Its mean is 743, and its standard deviation is 140. Okay, great. But what if the mean is smaller or bigger? Let's first zoom out a bit by adding the origin of the graph. The origin is the 0 point. Adding it to any graph gives perspective. Keeping the standard deviation fixed, or in statistical jargon, controlling for the standard deviation, a lower mean would result in the same shape of the distribution, but on the left side of the plane. In the same way, a bigger mean would move the graph to the right. In our example, this resulted in 2 new distributions. One with a mean of 470 and a standard deviation of 140, and one with a mean of 960 and a standard deviation of 140. Alright, let's do the opposite. Controlling for the mean, we can change the standard deviation and see what happens. This time, the graph is not moving, but is rather reshaping. A lower standard deviation results in lower dispersion, so more data in the middle and thinner tails. On the other hand, a higher standard deviation will cause the graph to flatten out with less points in the middle and more to the end, or in statistics jargon, fatter tails. Great! In our next lesson, we will use this knowledge to talk about standardization. Stay tuned!
Lecture 17, Standard Normal Distribution.
The standard normal distribution is a particular case of the normal distribution. We'll use the letter Z to denote it. It has a mean of 0 and a standard deviation of 1. The standard normal distribution is easy to understand and has several important applications. Every normal distribution can be standardized. Standardization in this context is the process of turning a normally distributed variable to one with a standard normal distribution. A simple formula allows us to do that. The standardized variable, the variable whose normal distribution we are turning into a standard normal distribution, is called a z-score and is equal to the original variable minus its mean divided by its standard deviation. Let's try to interpret it. First, we have to look at the numerator. If you take a dataset, subtract its mean from each data point, and then calculate the mean once again, you will get 0. The following example will help us prove that. Let's take an approximately normally distributed set of numbers. 1, 2, 2, 3, 3, 3, 4, 4, and 5. Its mean is 3, and its standard deviation, 1.22. Now, let's subtract the mean from all data points. We get a new data set of -2, -1, -1, 0, 0, 0, 1, 1, and 2. Let's calculate the mean. It is 0, exactly as we anticipated. Clear? Okay, great. So far, we have a new distribution, which is still normal, but with a mean of 0 and a standard deviation of 1.22. The next step of standardization is to divide all data points by the standard deviation. This will drive the standard deviation of the new dataset to 1. Let's go back to our example. Both the original dataset and the one we obtained after subtracting the mean from each data point have a standard deviation of 1.22. Remember, adding and subtracting to all data points does not change the standard deviation. Now, let's divide each data point by 1.22. We get minus 1.63, minus 0.82, minus 0.82, 0, 0, 0, 0.82, 0.82, and 1.63. If we calculate the standard deviation of this dataset, we will get 1. And the mean is still 0. Let's quickly show that. Cool. This is how we can obtain a standard normal distribution from any normally distributed dataset. Using it makes predictions and inference much easier, and this will help us a great deal in what we will see next. Thanks for watching.
Lecture 18, Understanding the Central Limit Theorem.
The central limit theorem is one of the most important concepts in statistics. If you had to choose one thing to remember from this course, which I hope you don't, what we'll see in this lesson is what you want to remember. The reason for this is the unmatched practical application of the theorem. Okay, let's get started then. Imagine that you are given a dataset. Its distribution does not matter. It could be normal, uniform, binomial, or completely random. The first thing you want to do is start taking out subsets from the dataset, or as statisticians call it, you start sampling it. This would allow you to get a better idea of how the entire dataset is made, right? Okay, once you have taken a sufficient number of samples and then calculated the mean of each sample, we'll be able to apply the central limit theorem. No matter the distribution of the entire dataset, binomial, uniform, or another one, the means of the samples you took from the entire dataset will approximate a normal distribution. The more samples you extract and the bigger they are, the closer to a normal distribution the sample means will be. Moreover, their distribution will have the same mean as the original dataset and an n times smaller variance, where n is the size of your samples you took from the dataset. Let's confirm the theorem with an example. We have prepared 960 random numbers from 1 to 1000. This is their frequency distribution, so you are sure that they are randomly picked. The mean of this dataset is 489, and its variance is 82,805. Let's extract 30 random samples out of the dataset, each consisting of 25 numbers. Remember when we said that the sample should be sufficiently large? A common rule of thumb is that the sample should be bigger than 25 observations. The bigger the sample size, the better the results you'll get. So we have our samples. Now we are going to calculate their means and plot them once again. Okay, excellent. It looks approximately normally distributed, doesn't it? Let's check if the other part of the theorem was right. The mean of our newly acquired dataset is 492, while its variance 3,171. Did we expect these numbers? We anticipated a mean of 489 and a variance of 82,805 divided by 25, so around 3,312. Well, when dealing with such big numbers, we almost get the mean right, and the variance was not that far off either. In the next few lectures, you will learn how to statistically confirm whether such small differences are close enough to the actual result we expect to obtain. Spoiler alert, they are, and we'll show you why. So we have learned the main idea behind the central limit theorem. The key takeaway from this lesson is that the number of samples taken tends towards infinity. The distribution of the means start approximating a normal distribution. Imagine their power if your dataset was made up of millions of values, and you could afford to sample just a tiny bit of them. We can be assuming normally distributed data almost all the time, and that's extremely helpful, as you will see later on. Okay, this will do for now. Thanks for watching.
Lecture 19, Standard Error.
In the previous lesson, we showed that no matter the underlying distribution of the dataset, the distribution of the sample means would be normal with a mean equal to the original mean, and a variance equal to the original variance divided by the sample size. Alright, this lecture will be very short and has the sole purpose of defining what a standard error is. The standard error is the standard deviation of the distribution formed by the sample means. So how do we find it? We know its variance, sigma squared, divided by n. Therefore, the standard deviation is sigma divided by the square root of n. Like a standard deviation, the standard error shows variability. In this case, it is the variability of the means of the different samples we extracted. You can guess that since the term has its own name, it is widely used and very important. Why is it important? Well, it is used for almost all statistical tests because it shows you how well you approximated the true mean. More on that in the next lessons. Note that it decreases as the sample size increases. This makes sense as bigger samples give a better approximation of the population. That's all for now. Thanks for watching.
Lecture 20, Working with Estimators and Estimates.
Okay, great. Let's continue by introducing the concept of an estimator of a population parameter. It is an approximation depending solely on sample information. A specific value is called an estimate. There are two types of estimates: point estimates and confidence interval estimates. A point estimate is a single number, while a confidence interval, naturally, is an interval. The two are closely related. In fact, the point estimate is located exactly in the middle of the confidence interval. However, confidence intervals provide much more information and are preferred when making inferences. Alright, have we seen estimates so far? Sure, we have. The sample mean, x bar, is a point estimate of the population mean mu. Moreover, the sample variance s squared was an estimate of the population variance, sigma squared. There may be many estimators for the same variable. However, they all have two properties: bias and efficiency. We will not prove them as the mathematics associated is out of the scope of this course. However, you should have an idea about the concepts. Estimators are like judges. We are always looking for the most efficient unbiased estimators. An unbiased estimator has an expected value equal to the population parameter. Let's think of a biased estimator to explain that point. What if somebody told you that you will have to find the average height of Americans by taking a sample, finding its mean, and then adding 1 foot to that result? So the formula is x bar plus 1 foot. Well, I hope you won't trust them. They gave you an estimator, but a biased one. It makes much more sense that the average height of Americans is approximated just by the sample mean, right? We say that the bias of this estimator is 1 foot. Clear? Okay, great. Let's move on to efficiency. The most efficient estimators are the ones with the least variability of outcomes. From the estimates we know so far, we haven't seen estimators with problematic variance, so it is hard to exemplify. It is enough to know that the most efficient means the unbiased estimator with the smallest variance. Alright, in the next lecture, we will explore confidence intervals, so stick around.
Lecture 21. Confidence Intervals, an invaluable tool for decision making.
Hi again. In the previous lesson, we learned about point estimators. But as you can guess, they are not very reliable. Imagine visiting 5% of the restaurants in London and saying that the average meal is worth £22.50. You may be close, but chances are that the true value isn't really £22.50, but somewhere around it. It's much safer to say that the average meal in London is somewhere between £20 and £25, isn't it? In this way, you have created a confidence interval around your point estimate of £22.50. A confidence interval is a much more accurate representation of reality. However, there is still some uncertainty left which we measure in levels of confidence. So, getting back to our example, you may say that you are 95% confident that the population parameter lies between 20 and 25 quid. Keep in mind that you can never be 100% confident unless you go through the entire population. And there is, of course, a 5% chance that the actual population parameter is outside of the 20 to 25 pounds range. We'll observe that if the sample we have considered deviates significantly from the entire population. Alright, there is one more ingredient needed: the level of confidence. It is denoted by 1 minus alpha and is called the confidence level of the interval. Alpha is a value between 0 and 1. For example, if we want to be 95% confident that the parameter is inside the interval, alpha is 5%. If we want a higher confidence level, say 99%, alpha will be 1%. Don't worry, we will discuss this in more detail in our next video. You can't wait until the next lesson? Okay then, here it is. The formula for all confidence intervals is from the point estimate minus the reliability factor times the standard error to the point estimate plus the reliability factor times the standard error. We know that the point estimate is values like x bar and s bar, right? We also know what the standard error is. What about the reliability factor? We'll have to introduce it in our next lesson.
Lecture 22. Calculating confidence intervals within a population with a known variance.
A confidence interval is the range within which you expect the population parameter to be, and its estimation is based on the data we have in our sample. There are two main situations when we can calculate the confidence intervals for a population: when the population variance is known and when it is unknown. Depending on which situation we are in, we would use a different calculation method. In this lesson, we will explore the confidence intervals for a population mean with a known variance. An important assumption in this calculation is that the population is normally distributed. Even if it is not, you should use a large sample and let the central limit theorem do the normalization magic for you. Remember, if you work with a sample which is large enough, you can assume normality of sample means. Alright, let's say you want to become a data scientist and you are interested in the salary you are going to get. You are also aware that population standard deviation of data science salaries is equal to $15,000. Furthermore, you know the salaries are normally distributed and your sample consists of 30 salaries. The formula for the confidence interval with a known variance is given below. The population mean will fall between the sample mean minus z of alpha divided by 2 times the standard error, and the sample mean plus z of alpha divided by 2 times the standard error. The sample mean is the point estimator. You know all about the standard error already, so let's compute it using the formula. What we have left is the so-called reliability factor, z of alpha divided by 2. Z is the statistic that we've described earlier, the standardized variable that has a standard normal distribution. Right. And what about alpha? This is the same alpha we had when we defined our confidence level. So, for a confidence level of 95%, alpha would be equal to 5%. Similarly, for a confidence level of 99%, alpha would be equal to 1%. It all falls into place now. Let's get back to our example. The sample mean is $100,200, and the standard deviation is known to be $15,000. Thus, the standard error is $2,739. Having calculated these values, we can take the next step and choose our confidence level. Common confidence levels are 90%, 95%, and 99%, with respective alphas of 10%, 5%, and 1%. Another way to put in the value of alpha is 0.1, 0.05, and 0.01 respectively. Keep in mind that a 95% confidence interval means that you are sure that in 95% of the cases, the true population parameter would fall into the specified interval. The z of alpha comes from the so-called standard normal distribution table. It is best to first see it and then comment on it. Let's say we want to find the values for the 95% confidence interval. Alpha is 0.05. Therefore, we are looking for z of alpha divided by 2, or 0.025. In this table, this will match the value of 1 minus 0.025, or 0.975. The corresponding z comes from the sum of the row and column table headers associated with this cell. In our case, the value is 1.9 plus 0.06, or 1.96. A commonly used term for the z is critical value. So, we have found the critical value for this confidence interval. Now, we can easily substitute in the formula. The final confidence interval becomes 94,833 to 105,568. The interpretation is the following. We are 95% confident that the average data scientist salary will be in the interval 94,833 and $105,568. Let's repeat the exercise using a higher confidence level. Say we want to be 99% certain of the outcome. Alpha is 0.01. We look at the table for the value of 1 minus 0.005. Which is equal to 0.995. Bummer! There is no such value. When this happens, we just have to round to the nearest value available. The corresponding critical value is 2.5 plus 0.08, thus 2.58. We plug it into our formula once more, and the new confidence interval is equal to 93,135 and 107,206. This means that we are 99% confident that the average data scientist salary is going to lie in the interval between $93,135 and $107,206. Please note that in this case, there is a trade-off between the level of confidence we chose and the estimation precision. The interval we obtained is broader. The opposite is also true. A narrow confidence interval translates to higher uncertainty. Makes sense, right? If we are trying to estimate the population mean and we are picking a larger interval, we are increasing our chances of having an interval that actually includes the mean. And vice versa. If we want to be more specific about the population mean range, this will take away from our confidence about this statement. Okay, this lecture was a bit longer, but very insightful. Don't skip the exercises provided. They will help you reinforce the knowledge about this concept, which is fundamental for everybody who wants to work with numbers in their job. In the next few lessons, we will study some particular cases and teach you how to find confidence intervals for them. Thanks for watching.
Lecture 23, Student's T-Distribution.
It's time for a short break from all these numbers and calculations. I would like to tell you a story. William Gossett was an English statistician who worked for the brewery of Guinness. He developed different methods for the selection of the best yielding varieties of barley, an important ingredient when making beer. Gossett found big samples tedious, so he was trying to develop a way to extract small samples but still come up with meaningful predictions. He was a curious and productive researcher and published a number of papers that are still relevant today. However, due to the Guinness Company policy, he was not allowed to sign the papers with his own name. Therefore, all of his work was under the pen name Student. Later on, a friend of his and a famous statistician, Ronald Fisher, stepping on the findings of Gossett, introduced the T-statistic, and the name that stuck with the corresponding distribution even today is Student's T. The Student's T-distribution is one of the biggest breakthroughs in statistics, as it allowed inference through small samples with an unknown population variance. This setting can be applied to a big part of statistical problems we face today, and is an important part of this course. Alright, visually, the Student's T-distribution looks much like a normal distribution, but generally has fatter tails. Fatter tails, as you may remember, allows for a higher dispersion of variables, as there is more uncertainty. In the same way that the z-statistic is related to the standard normal distribution, the t-statistic is related to the Student's T-distribution. The formula that allows us to calculate it is t with n-1 degrees of freedom and a significance level of alpha equals the sample mean minus the population mean, divided by the standard error of the sample. As you can see, it is very similar to the z-statistic. After all, this is an approximation of the normal distribution. The last characteristic of the Student's T-statistic is that there are degrees of freedom. Usually, for a sample of n, we have n-1 degrees of freedom. So, for a sample of 20 observations, the degrees of freedom are 19. Much like the standard normal distribution table, we also have a Student's T table. Here it is. The rows indicate different degrees of freedom, abbreviated as DF, while the columns, common alphas. Please note that after the 30th row, the numbers don't vary that much. Actually, after 30 degrees of freedom, the t-statistic table becomes almost the same as the z-statistic. As the degrees of freedom depend on the sample, in essence, the bigger the sample, the closer we get to the actual numbers. A common rule of thumb is that for a sample containing more than 50 observations, we use the z-table instead of the t-table. Alright, great! In our next lecture, we will apply our knowledge in practice.
Lecture 24, Calculating Confidence Intervals Within a Population with an Unknown Variance.
Alright, so we've learned that confidence intervals based on small samples from normally distributed populations are calculated with the t-statistic. Let's revisit the example we saw earlier. You are an aspiring data scientist and are wondering how much the mean data scientist salary is. You have a sample of 9 compensations you found on Glassdoor, and you have summarized the information in the following table. Okay, we've already calculated the sample mean and standard error, which are $92,533 and $4,644 respectively. But this time we don't have one key piece of information, the population variance. No problem. As the good statisticians that we are, we will use the Student's T-distribution. Here's the formula that allows us to find a confidence interval for the mean of a population with an unknown variance. Let's compare it with the formula we used when the variance is known. There are 2 key differences. First, instead of z-statistic, we have a t-statistic. And second, instead of population standard deviation, we have sample standard deviation. Otherwise, everything is the same. So, it shouldn't be that difficult to remember. The logic behind constructing confidence intervals in both cases is the same. The only two inputs that change are the statistic at hand and the standard deviation. When population variance is known, population standard deviation goes with the z statistic. When population variance is unknown, sample standard deviation goes with the t statistic. Alright, so we have the sample mean, standard deviation, and sample size. All we have to do is find the t statistic. We will be able to obtain the t statistic from the t-table. First, we need to specify the degrees of freedom. For the student's t-distribution, there are n-1 degrees of freedom. Our sample consists of 9 observations, so we have 8 degrees of freedom. Second, we have to find alpha divided by 2. Once again, this depends on the confidence level that we want to obtain. In this example, we are going to use a confidence level of 95%. This means that alpha is equal to 5%. Therefore, half of alpha would be 2.5%. You can now see that the associated t-statistic is 2.31. Great! Note that some t-tables you will find in books or online, like this one, have a CI row. The abbreviation stands for confidence interval. Instead of finding alpha, we can just check the 95% confidence interval and get the same result. Easy. Okay, we have all the information needed, so we just plug in the numbers. What we get is a confidence interval from $81,806 to $103,261. Let's compare this result to the result for the confidence interval with known population. We got a 95% confidence interval that was between $94,833 and $105,568. You can clearly note that when we know the population variance, we get a narrower confidence interval. When we do not know the population variance, there is a higher uncertainty that is reflected by wider boundaries for our interval. Makes sense, doesn't it? So, what we learned today is that even when we do not know the population variance, we can still make predictions, but they will be less accurate. Furthermore, the proper statistic for estimating the confidence interval when the population variance is unknown is the t-statistic and not the z-statistic. Alright, great! Thanks for watching!
Lecture 25, What is a margin of error and why is it important in statistics?
Welcome back! In the last few lessons, we've been concentrating on confidence intervals. We learned about two situations, when the population variance is known, which happens very rarely in practice, and when the variance is unknown and follows a student's t-distribution. The goal of this lesson is less about learning and more about clarifying. Alright, these are the formulas that allow us to find confidence intervals. As we noted in our previous lecture, these parts are the ones that determine the span of the confidence interval. There is a special name for these expressions: margin of error. When the population variance is known, the margin of error is equal to this expression, and in the case of population variance unknown, the margin of error is equal to this expression instead. So, basically, the confidence intervals could be summarized as follows. The true population mean falls in the interval defined by the sample mean plus minus the margin of error. Now, we get to the core of this lesson. Getting a smaller margin of error means that the confidence interval would be narrower. As we want a better prediction, it is in our interest to have the narrowest possible confidence interval. The best part is that we can actually control the margin of error. Let's see its parts. There is a statistic, a standard deviation, and the sample size. The statistic and the standard deviation are in the numerator, so smaller statistic and smaller standard deviations will reduce the margin of error. How do we do that? A higher level of confidence increases the statistic. A higher statistic means a higher margin of error. This leads to a wider confidence interval. Think about this example. You took an exam and you want to make a prediction about the mean grade obtained by all exam takers. As A, B, C, D, and F are all possible grades, we are 100% confident that the mean grade will be in the confidence interval from F to A. Now, if we lower the confidence level to 99%, we may end up with a confidence interval from F plus to A minus. Remember the interpretation. In 99% of the cases, the population mean falls in the interval. So, with a 50% confidence level, in 50% of the cases, the true mean will fall in the specified interval. The only scenario under which this is possible is if the interval is narrower. Therefore, if the standard deviation and the sample size are kept constant, a lower confidence level will result in a narrower interval. What about the standard deviation? That's easy. A lower standard deviation means that the dataset is more concentrated around the mean, so we have a better chance to get it right. For instance, the mean grade in your class is B, and you know that there were people with A's, B's, C's, D's, and a few F's. How likely is it that you got a B? Now, compare this to a situation when the teacher said, the mean of the class is around B, and the lowest grade is C. In this case, you are much more likely to get a B, right? In the first case, the grades are dispersed, while in the second, they are concentrated. Lastly, we have the sample size in the denominator. Higher sample sizes will decrease the margin of error. This is also quite intuitive. The more observations you have in your sample, the more certain you are in the prediction. This time, you have a B+. There are 30 people in the class, and you want to know if you performed above the average. You ask 3 of your friends, and they all got A's. Your sample of 3 people leads you to think you underperformed. You get frustrated and start asking around some more. The next 5 people you ask got D's. Now you have a sample of 8 people, and it seems you did quite well. After asking everyone in class, the whole population that is, you find out that the mean grade is B. You are above average by a small margin. The conclusion is that the more observations there are in the sample, the higher the chances of getting a good idea about the true mean of the entire population. Alright, hopefully this clears up some doubts you may have had. Thanks for watching.
Lecture 26: Calculating confidence intervals for two means with dependent samples.
So far, we have talked about confidence intervals with population variances that are either known or unknown. However, we were considering only one population. In the next couple of lessons, we will explore confidence intervals looking into 2 populations. These cases are more important as they have a wide range of real-world applications. A few important distinctions need to be made before we dive into this topic. In some cases, the samples that we have taken from the 2 populations will be dependent on each other, and in others they will be independent. Dependent samples are easier. You will experience this firsthand. When we have independent samples, however, we can further distinguish 3 cases. When the population variance is known, when the population variance is unknown but assumed to be equal, and when it is unknown and assumed to be different. Sounds a bit overwhelming, but don't worry. In statistics, many concepts are similar to each other, and you will quickly see that you have already acquired the intuition that allows you to understand these concepts pretty fast. Alright, let's get on to the first case, namely dependent samples. This statistical test is often used when developing medicine. Let's say you have developed a pill that increases the concentration of magnesium in the blood. It is very promising, but there is no data to support your claim. After testing the drug in the laboratory, it is time to see its actual effect on people. What you would typically do is take a sample of 10 people and test their magnesium levels before and after taking the pill. The 2 dependent samples are the magnesium levels before and the magnesium levels after. It is clear that it is the same people we are testing. Thus, the samples are dependent. An important note is that the populations are normally distributed. Actually, when dealing with biology, Normality is so often observed that we immediately assume that such variables are normally distributed. Okay, back to the example. Whenever you take a blood test, the magnesium levels are stated in milligrams per deciliter, and a healthy person would usually have somewhere between 1.7 and 2.2 milligrams of magnesium per deciliter. Here is a table that contains the sample of 10 people and their levels of magnesium before and after taking the pill for some time. We've also added a cell that calculates the difference in levels before and after taking the pill. Instead of dealing with two variables, we now have only one. In this way, the data looks as a single population, doesn't it? Let's calculate the mean and the standard deviation of the differences. The mean is 0.33 and the standard deviation is 0.45. Moreover, we know that the sample size is 10. The formula that would allow us to calculate a confidence interval is the following. The population is normally distributed, but the sample we have contains only 10 observations. Therefore, the distribution we'll have to work with is students T, and the appropriate statistic is T. You can clearly see that it is the same as the one for a single population with an unknown variance. Let's choose a level of confidence and plug in the numbers. As we have said many times, 95% confidence is one of the most common levels, and so we will use it here as well. The T statistic with 9 degrees of freedom for a 95% confidence interval is 2.26. Now, we have everything we need and we can calculate the confidence interval. It lies in the range between 0.01 and 0.65. How do we interpret this result? Well, in 95% of the cases, the true mean will fall in this interval. Moreover, the whole interval is positive. This shows that the true mean of the difference is definitely positive. Therefore, with 95% certainty, we can say that the levels of magnesium in the test subject's blood is higher. The purpose of this test was to determine whether the drug is effective. Based on our small sample, it most likely is. Alright, this shows you some of the practical applications of inference. Stay tuned for our next lesson, in which we will explore confidence intervals on independent samples.
Lecture 27, Calculating Confidence Intervals for Two Means with Independent Samples, Part 1.
In our last video, we learned about confidence intervals for two means based on dependent samples. In this video, we will explore independent samples. As we said earlier, there are three sub-cases: known population variances, unknown population variances but assumed to be equal, and unknown population variances that are assumed to be different. Here we will focus on independent samples with known population variances. Alright, let's jump right into the example that would allow us to understand the concept a bit better. We would like to get the test grades of two departments in a UK university. University grades in the UK expressed in percentages. Our samples are taken from two departments: engineering and management. The table you see here summarizes the data. We have a sample of 100 engineering students, and the average grade is 58%. From past years, we know that the population standard deviation is 10 percentage points. Thus, the variance is known. We also have a sample of 70 students from the management department, and we've got a sample mean of 65%. Again, from past data, we know that the population standard deviation is 5%. Okay, but before we get on with calculations, let's point out three important considerations. First, the populations are normally distributed. Second, the population variances are known. And third, the sample sizes are different. Different sample sizes are a common occurrence in the real world. In our previous lesson, when we had dependent samples, we were testing the same people over time, so it made sense that the sample sizes were equally big. This time, however, the observations are completely different. They are students from different departments, with different teachers, obtaining different grades when taking different exams. The grade of a person from engineering doesn't in any way affect the grade of a person studying management, right? The two samples are truly independent. Alright, what are we testing? We want to find a 95% confidence interval for the difference between the grades of the students from engineering and management. As with every confidence interval, we must identify the test statistic. Samples are big, population variances are known, and populations are assumed to follow the normal distribution. All this information points us to the z statistic instead of the t. The last ingredient is the variance. We haven't been through enough mathematics in this course to derive the formula, so we will simply state it. The variance of the difference between the two means is equal to the variance of the grades received by engineering students divided by the sample size of engineering students, plus the variance of grades obtained by management students divided by the sample size of management students. The underlying logic is that dispersion is additive. More variables means higher or equal variability. Okay, so what is the confidence interval formula this time? Well, it is given by the expression below. X bar minus Y bar is the difference point estimator. Z is the statistic, and this is the variance of the difference. We plug in the numbers and get a confidence interval between minus 9.28 and minus 4.72. Alright, what's the interpretation? We are 95% confident that the true mean difference between engineering and management grades falls into this interval. Note that this time the whole interval is negative. This is because we were calculating engineering grade minus management grade. As the engineers were consistently getting lower grades, the difference is negative. Had we calculated the difference as management minus engineering, we would have obtained a confidence interval between 4.72 and 9.28, completely symmetrical around 0. Alright, great. Remember to do all the exercises available in the course materials, as the topics are getting tougher and tougher. See you next time, and thanks for watching.
Lecture 28, Calculating Confidence Intervals for Two Means with Independent Samples, Part 2.
Hi again. In the last few lessons, we've been focusing on confidence intervals. We'll do that here too. This lesson is about independent samples with variances unknown but assumed to be equal. Alright, think about this example. You are trying to calculate the difference of the price of apples in New York and LA. You go to 10 grocery shops in New York, and your friend Paul, who lives in LA, visits 8 grocery shops in order to help you with the research. Once you've organized the data in a table, you start reflecting on how you can create a confidence interval that shows the difference between the price of apples in New York and LA. You don't know what the population variance of apples in New York or LA is, but you assume it should be the same for NY and LA. So, you calculate the mean price in NY and LA and obtain $3.94 and $3.25 respectively. Moreover, their sample standard deviations are 18 cents and 27 cents. What should we do now? Well, we assume that the population variances are equal, so we have to estimate them. The unbiased estimator in this case is called the pooled sample variance, and we could use the following formula to calculate it. As you can see, it is based solely on the sample sizes and the sample standard deviations of the two datasets. We quickly plug in the numbers and get a pooled sample variance of 0.05 and a pooled standard deviation of 22 cents. How about the statistic needed to form a confidence interval? Well, we have an unknown variance, so you guessed it, it's the t statistic. Here's the formula for the confidence interval. Let's compare it to the formula for independent samples with known variance. We have the same difference of sample means. For the variances, instead of population variances, we have the pooled sample variance. And then, instead of the z statistic, we have the t statistic. Although the formulas are different, they are very consistent, right? You must be wondering about the t statistic though. It is a bit stranger this time, So let's quickly try to clarify it. The degrees of freedom are equal to the total sample size minus the number of variables. So far, we have seen t's with n-1 degrees of freedom because we had a sample size of n and only one variable. This time, we have two sample sizes, one of 10 and one of 8 observations, and two variables, apple prices in New York and apple prices in LA. Therefore, we have 16 degrees of freedom. Alright, checking the t statistic from the table for a 95% confidence interval with 16 degrees of freedom, we get 2.12. Let's plug everything in and get our answer. The 95% confidence interval is between 0.47 and 0.92. What's the interpretation? Well, we are 95% confident that the actual difference between the two populations, price of apples in New York and in LA, is somewhere between 0.47 and 0.92. Therefore, it is clear that apples in New York are much more expensive than in LA. Good job, and thanks for watching.
Lecture 29 Calculating Confidence Intervals for Two Means with Independent Samples Part 3.
Hi, and welcome back. This is the last lesson about confidence intervals. We are not going to get too deep into it as it is just about knowing the formula. Sometimes, we want to find the confidence interval for two sample means when the samples are independent, with unknown variances, and when the variances are assumed to be different. You can think about comparing apples and oranges. You've heard the expression, right? Well, in statistics, if you actually want to compare apples and oranges, this is the right way to do it. Here's the confidence interval formula. Once again, we have the differences of the means of the two samples. The variances are the sample variances of each of the two variables, and here are the respective sample sizes. The tough thing about this is to estimate the degrees of freedom. Well, statisticians have come up with a formula that allows us to do just that. You have all the information, but it is highly unlikely that you will remember the formula. Alright, we won't give an example of this case, as it won't add any value to this course. In this video, we just wanted to show you the right way to compare apples and oranges. Next time, we will get to the core of statistics, hypothesis testing. Don't miss out, and thanks for watching.
Lecture 30 Practical Example _ Inferential Statistics.
Hi, and welcome to our second practical example. Let me introduce you to the topic. You are a data analyst for Al Bundy's shoe shop. Al Bundy's is a US-based company established 30 years ago. It also operates in Canada, the UK, and Germany. The firm sells mid to high-end shoes, ranging from $120 to $200. While the shoes are of high quality, you have lots of inventory never sold. The shoes collect dust on store shelves. Inventory management is a common problem. Many, if not most shops cannot determine the right number of items they need to keep in stock. The opposite problem arises too. Shops don't supply an adequate amount of goods and fail to meet the demand in their market. For instance, you have surely entered a shoe shop but could not buy a specific pair of shoes because they did not have them in stock. In this example, we will examine the opposite problem, having too much inventory. This is a more significant problem for the company, as it means the company has invested in producing or purchasing the product but could not sell it. Alright, one way to solve this problem is by using confidence intervals. We have seen many examples, but here's a real-life one. We can see a database with the sales information about Al Bundy's shop for the years from 2014 to 2016. There's invoice number, date, country, product ID, and shop, which depends on the country. The cell gender indicates if the product is designed for men or women, as shoes differ greatly depending on gender. Next, we have shoe size. Apart from the US size system, I have also included the European and the UK ones, so it is easier for you to understand the data if you are used to the other systems. This file will be provided for you, and you can check the shoe size conversion table if you would like to do that. Finally, there's the unit price for that sale and the discount that applies. Let's begin our analysis. First, we should determine if that's sample or population data. It's obviously a sample, not the population of sales, given we have just 3 years of data. Second, we want to get to know the dataset better. There are 2 big subgroups in our data: men's shoes and women's shoes. They are different, and bundling them when making predictions will yield deceiving results. Not only feet differ by gender, but also there are different shoe types and models. Our problem is related to inventory management. Therefore, we should divide our inventory and then count the frequencies. The frequencies will give us a better idea of the data. Okay, a good way to do that is to divide the data by shoe size. I would also like to see it country-wise. We already noted division by gender is also needed. So we have 3 dimensions: shoe size, country, and gender. A possible solution is to create 2 tables, one for men's shoes and one for women's shoes, and then proceed normally. That's what I will do. Here are the 2 tables. In the file provided in the resources section, you can see the formula I used to calculate the frequencies. While Excel may be sloppy, it is still powerful. To use confidence intervals, we must have normally distributed data. While this sounds restrictive, for all practical applications, it isn't. We can simply apply our good old friend, the central limit theorem. When we are in the presence of a sum or average of many observations, we can assume normality. In our case, we are calculating average sales for a period. Given that Al Bundy's shop has been operating for over 30 years, CLT applies and we can safely continue with our inference. Okay, we want to estimate the number of shoes that are likely to be sold. A 95% confidence interval will give us such information. We will take the last 12 months of sales and make a prediction. Let's do this only for men's shoes, as the main problem is identical for both genders. Since people have different shoe sizes, we will have to calculate 17 confidence intervals, one for each size. Let's get to it. First, we need to calculate the means. Here they are. Next, we do not know the population variance, and our sample comprises just 12 observations. We have to use the t-statistic. This problem refers to the lesson on one population with population variance unknown. We have a sample of 12 observations. Therefore, we are looking for the t-statistic for a 95% confidence interval with 11 degrees of freedom. It is 2.18. Next, we will compute the standard errors. We will use the good old formula. While it is unnecessary to go through this step, as we have everything we need, I will still show you the margins of error, as it may be interesting for some of you to examine. Finally, the confidence intervals are given by the following formula. And this is how they look after the calculations have been carried out. The result we obtained could be interpreted as follows. In 95% of the cases, the true population mean of the sales for each shoe size will fall into the respective interval. As we don't want to be low on stock, a possible solution to the problem is to get as many pairs of shoes as the closest number to the upper limit of the confidence interval. In this way, you will be almost certain you won't run out of stock and shoes won't be waiting forever in your storage unit. Therefore, we should get 4 pairs of men's shoes size 6, 3 pairs of men's shoes size 6.5, and so on. Mostly, we should prepare ourselves with size 9.5, and size 16 won't yield in any sales. Sorry for those of you with size 16 feet. I know it is hard enough to find shoes, but this company won't be selling any. Alright, we are almost done here. Before you go, I'd like to show you another application of confidence intervals. Let's say we want to use a confidence interval to see if 2 shops are selling the same number of shoes. We want to know with 95% confidence by how much one shop outperforms the other in terms of sales. You can see 2 tables representing the sales of women's shoes in 2 German shops. Their codes are GER1 and GER2. Once again, we have data for 2016. Now, an assumption we have to make is that the same people don't buy pairs of shoes from different shops. Logically, it makes sense that in the same year, the same people don't go around different shops of the same brand to buy shoes. Even if this happens, it is an exception, not the norm. Therefore, we can say that two samples are independent. Once again, we don't know the population variance, but given this is the same market in the same country, we can assume it is equal. This implies we are in the case of independent samples with population variance unknown but assumed to be equal. Like in the previous case, we need to calculate the means and the sample variances. Here, we must calculate a pooled variance, which is an unbiased estimator of the population variance. We are in the case where we have to use the t-statistic with 12 plus 12 minus 2 degrees of freedom for a 95% confidence. What we get from the table is 2.07. The respective margins of error are given by the well-known formula. Finally, the 95% confidence intervals are determined by the means and the margins of error. We get these 15 intervals. 0 is a part of all of them. Except for the unsellable size 4, all confidence intervals start in the negatives and finish in the positives. This implies we cannot conclude one shop sells more shoes than the other for any size. What it seems like we have no great insight, that's not entirely true. The confidence intervals we got are not consistently for one shop having higher sales or the other. This is evident from the fact that some are mostly negative, while others are mostly positive. That is to show that, for some sizes, GER1 is likely to sell more, while for others vice versa. However, our decision was that, using this methodology and level of confidence, we cannot really identify which shop is selling more. They are identical. The insight we get is these two shops are so balanced in sales they may share the same warehouse or exchange pairs of shoes to achieve better results. They can be bundled together for any analysis, action, or decision needed. On average, they will probably move together. If one noticeably outperforms the other, we may be sure something that wasn't observed before is going on, as they are predicted to remain identical. Alright, time to wrap up this lesson. In the next section, we will examine hypothesis testing. Thanks for watching.